I'm going to continue where Olaf left it. It's about RD Connect. As I've told you, RD Connect is a similar project that tries to connect, as the title says, between a database, registries, biobank, and clinical bioinformatics. I would say genome informatics for rare disease research. So, as Olaf said in his talk, RD Urinomics, RD Neuromics, and RD Connect is a 38 million euros project funded by the European Commission that's going to last until the end of 2018. And the plan is to tackle genetic disease. And all this is under the umbrella of a consortium that is known as IRDIC, which stands for International Research Disease International Consortium. RD Connect, in brief, it's consisted of 7 work packages. The coordination comes from Newcastle by Professor Hans Lochmuller, and it involves the coordination of the project. You have the work package 2, which involves the patient registries, work package 3, which has to do with biobanks, work package 4 and 5, which are the most, let's say, core work packages in this project. Bioinformatics, led by Christophe Beroux from Montpellier, and the unified platform that it's going to be designed under the coordination of Ivo Gut from Barcelona. And finally, you need 2 important aspects. One is to address the ethical, legal, and social issues, the so-called ELSI, and that's coordinated by Mats Hansen from Uppsala University. And finally, the impact and the innovation and also the dissemination of these activities that is coordinated again by Newcastle, by Professor Kate Busby. And that's actually the approval by her and her colleagues which made this workshop possible today. So I have decided to present you some of one of the cornerstones of RD Connect, which is how you provide incentives to share genetic variation data, and that is known as the microattribution approach, in which, of course, Doug has significantly contributed when this project has been implemented. So the post-genomic era resulted in an exponential increase of genome variation data production. And to be able to address this, you need genetic databases, which are publicly available online repositories of genome variation data that are described for a single gene, known as locus-specific databases, or LSDBs, more genes up to the whole genome, and these are the general databases. One of the most comprehensive ones is curated by David Cooper in Cardiff. It's known as HGMD. And those databases are specifically designed for a specific population ethnic group, and these are known as national genetic databases. And these are some of these. Most known ones are LOVD, Gen2Fen, that was the project that encouraged the development of several of those databases, UMD, Cafevarium, GWAS Central, and FindBase, the latter involving national genetic databases. Now, when we have a genetic mutation finding, we have the option or either share it with the scientific community, with a friend, with a colleague, or to keep it in the drawer, because we can't publish anymore single nucleotide substitutions. And worse, if we make it clearly unavailable to everybody else. So therefore, we need to find incentives to people to contribute their unpublished data, because as I'm going to show you in the next slides, these data by themselves may mean nothing, but if you put them together, may mean something. It can be very meaningful. So there have been some initiatives. One has been the Way Station project that was conceived by Dick Cotton several years ago. This project didn't go further; it died on its birth. There are several projects that have been tried to link a database with a journal. They worked theoretically, but in the end, they didn't go any further. And recently, it has been proposed the approach of microattribution from Nature Genetics. So the concept of microattribution is to produce a publication workflow. This is exactly how it has been described in this paper in 2008. To produce a publication workflow that is open to all journals, is very generic, and that draws on the expertise of all those with a stake in understanding variation at a particular region of the genome. And this concept would involve two components. The first would be a public genome browser that will display the actual number of the articles and the database entries. And the second component would be a high-profile article that will summarize the phenotypes of these variants. That means that it's not necessary to just have one variant without having the clinical information that accompanies it. And one of the fundamental requirements is that all the underlying data, genotype, phenotype data, should be made available in stable, publicly available databases, such as NCBI or EBI. Now, we have tried to implement the project by using one of the most comprehensive databases that are available today, and that's the Globin database, which is known as HBVAR. So the concept would be that you have several submissions that they come either from the public literature or they come from individual researchers. So the data would be not available in PubMed. But we had to find some way to identify that this contribution has been given by this particular person. And that's why we came across the researcher ID. You can get your researcher ID free of charge from researcherid.com. That's a Thomson Reuters venture. It's in 2-3 simple steps. So once you contribute this data, they go into this Globin gene server, which is a database, and they are converted into 4 microattribution tables. And the data will go out either at the public laboratory, which is NCBI or EBI, and or a scientific journal. And in that particular case, it was the first project, the data went into Nature Genetics, which was a high-profile publication. So the 4 microattribution tables would contain the submission of the SNPs to the central depository. The second table would have the information needed for microattribution, that is researcher and or PubMed ID. The third table would be the information on the phenotype and the clinical condition, and the 4 would be the information on the rare allele frequencies of the variants, if available. So each micro publication or nano publication, it's like a sentence that includes the subject, the verb, the object, the feature, and the citation. In principle, who said this sentence? And you can have this for locus-specific databases, as it is here. So this variant leads to beta thalassemia. That's a phenotype, a condition, and this is a researcher ID who has contributed this information. And if you go back to the HBVAR database, this is how the query would look like. So this is the thalassemia, this is the variant, and that's the phenotype, right? And if you go to the national genetic databases, then you have, again, in the same paradigm, that this variant has frequency of 80.5% in the population of Ghana, and that's a researcher ID of the person who has made this contribution. And again, if you look in FindBase, which is the database for clinically relevant genome variant allele frequency, this is how this would look like. This is a data entry, and here, I'm sure you can't see it, but believe me when I'm saying that this is actually the researcher ID, and this is the frequency, somewhere here. Now, I want to show you how, in fact, what I told you in the beginning, how important it would be to contribute your unpublished data, because together they can make sense. If you put together promoter variants in the fetal globin genes, in the human fetal globin genes and the human adult genes, you'll see there is a kind of splitting between the ones that they are found in the proximal promoter of the adult genes and those that are found in the distal promoter of the fetal genes. We don't know what this means, but we believe that this type of compartmentalization, let's say, of variants is because variants in this particular place in the proximal promoter would be most likely lethal for the embryos. That's why we can't find. So that's, of course, one speculation. Another thing that you can see from here is that they all cluster in transcription factor binding sites, and you can see here. And if you focus closer, you see that in the human beta globin gene, you see that they all cluster in transcription factor binding sites, ubiquitous or erythroid specific. These are the published data, and these are the unpublished data that have been contributed by microattribution. And the same thing would be the case for the gamma gene. Of course, one referee said that since you're claiming that this would be potentially functional, you have to prove it. That was actually quite difficult when we saw that comment. So we did transgenic mice exploiting Ken Peterson's constructs in Kansas. And when we made transgenic mice bearing this particular mutant, we've seen that these mice have indeed increased level of fetal hemoglobin, as you can see here. So that's the control, that's the positive control where you see high levels of fetal hemoglobin, and here you see that the levels are indeed high, as you can see here. So we were able to prove this to make the referee happy and to allow us to publish the paper in Nature Genetics. Another important gene, it's CLEF1. And that was actually a big contribution by Joseph Borge, who's sitting in the audience over there, relaxed, hopefully awake. So that's basically an LOVD that we have made for the CLEF1 gene. If you put all the variants together, you see, for example, that these particular ones lead to high levels of fetal hemoglobin. This is the one found in a Maltese family, with summary here. These are the controls. You see that most of the variants on the CLEF1 gene lead to moderate or high levels of fetal hemoglobin. And that's also a different application by clustering variants of the ATRX gene that Doug mentioned in his talk. Actually, he mentioned in the question that leads to alpha thalassemia mental retardation, an X-linked chromatin remodeling factor. And as you can see here, they're all clustered in different functional domains of the ATRX protein. These are variants lead to the ATRX syndrome in red. The green are variants that lead to alpha thalassemia and myelodysplastic syndromes. And then you have in yellow variants lead to both of these syndromes as shown above. Microattribution has also contributed to the increase of data submission. As you can see here, this is the year where microattribution has been launched, and you can see that the number of variants contributed compared to the other years is really higher. And this is a cumulative number of the variants submitted the year that microattribution has been launched. So Barend Mons from the Netherlands, from Leiden, has written a very nice paper that accompanied our article in 2011 in Nature Genetics, saying that what is the difference between a narrative article, a traditional article, and a nano publication. So a traditional article has a number of reads. So a narrative article doesn't support data sharing. A narrative article doesn't support and are not used the claims to be made for citation metrics. A regular article doesn't have a proper unique identifier ID. It doesn't support from the tables to deliver data mining, and I'm showing you this example in a minute. But if you go to the nano publication, you see that narrative articles are here. And then nano publications allow a data sharing. They allow claims to be made from them, and they can lead to citation metrics. And they can also allow to have a proper ID, data mining annotation from the tables, the nano publication tables that I've shown you. And as an example, he took our article and he made some measurements. And he found that if you would just do a text mining on that particular article, you just get 700 micro-publications from which only 13 would directly ascertain genomic variation. However, if you go back to the microattribution tables, you would be able to make 40,000 micro-publications with meaning to geneticists and with a proper citation potential. Now, this concept has been replicated in a clinical genetic databases. A paper that has been led by Gary Cutting from Johns Hopkins University. Milan also has been a significant contributor for that. And that article was published 2 months ago in Nature Genetics, and that was known as the CFTR project, which included 40,000 cystic fibrosis patients worldwide. This again shows that microattribution can incentivize clinicians to contribute the data to make this database available. The next step was also an initiative that is known as National Genetic Database Initiative. And this is basically a collaboration we also had with a colleague from Morocco, Ilham Ratbi. She has a lecture on Tuesday. I'm not sure if she's the audience. But in any case, this is the way to create a database based on unpublished information that is available in the country. And this is basically the Ethnos software, as it's called, for a software that we developed to support the development of Ethnos, of national genetic databases. So to conclude and to give over to Milan to finish this workshop, microattribution has incentivized indeed the submission of all genetic variation in a defined system and increased the reporting of human variants. And that led to the comprehensive online resource of human genetic variation in the globin and other genes that can lead to hemoglobinopathies and thalassemias. The same was also true for cystic fibrosis, as I've shown you. This approach also shown that data contribution in comprehensive databases that are interrelated would pose and answer questions that would otherwise not have been addressed, and that this leads potentially to interesting insights into normal biological processes. And finally, this can serve as an example that would lead to similar ventures in other systems, but also to document genomic variants for common or polygenic genetic traits. And this is the acknowledging slide of the people that have participated in this exercise, the initial verification of microattribution. Dr. is somewhere here. Thank you very much again. And I'd like to finish and give over the floor to Professor Maciek to end this workshop. Thank you very much. Unless there are any questions. Okay, please.
Okay, good afternoon, and thanks to everybody who remained for the last part of this workshop. And if I may get exactly. And the subject of my talk is to show you how to translate all these fantastic research issues which you heard today in the morning into clinical practice. And I would talk about the organization of care for genetic diseases in Europe and exemplify it on a couple of examples. So what we go through currently today is a life science data explosion nicely shown by Olaf. And you may recall from the London Tube, the announcement, Mind the Gap, and it's quite common there between the platform and the train. And you can show that the data which we are producing are just shooting through the roof, while the gap between the data and the information which you can get out of it, something meaningful which you can work with is like this. And the knowledge that is something which gets into textbooks and which is propagated further and seminal for other research pathways and so on. Again, the gap is further down here. And the clinical utility, that means that you get something out of the genome which has an impact on the treatment, again nicely exemplified by a couple of examples by Olaf, is again down here. So there's really a lot of translational issues to be solved down the way from research to diagnostics and further to treatment. Now, what are the aims of genetic services? The genetic services, in a broader sense, the main aim is to respond to the needs of individuals and families who are threatened by a genetic disease or who are at particular risk of developing or transmitting a disorder with a genetic component. And what was nicely shown by the introductory lecture by Professor Cooper is that we in fact deal with family-focused services, unlike our colleagues, not only neurologists, ophthalmologists, and so on. Usually the doctors are used to basically deal with a certain case, diagnose it, treat it, then they clip the folder together and put it into the locker. So the issue is, what is medical genetics? That's what we who remain here in the room are involved in. And what is genetics in medicine? And I would like to show you on a couple of examples how this is reconciled. Now, what is the specificity of genetic services? That's the rapid transfer from research to clinics. Again, I don't want to go into detail because all I have shown. But also sharing of expertise and experience, databases, again, demonstrated by George. Now, First, I would like to briefly touch the activities of the European Society of Human Genetics, which I was happy to chair a couple of years ago. I mean, and it's a non-profit organization like the American Society of Human Genetics, which promotes science, but also which promotes good clinical practice. And it's well known that the European Society organizes conferences, annual conferences, which are widely attended. We now reach almost 3,000 participants, which is quite a lot, starting from a couple of hundred 10 years ago. And what is less known is that a large part of the profits of this conference go towards fellowships for young scientists, which are now mainly targeted on the Eastern Mediterranean, and we will be more than happy to welcome also your young students from the Gulf. And also there's the activities of the Professional and Public Policy Committee, which addresses certain burning issues, not only LZ, the ethical and legal, but also practical issues, such as the one on calling for restraint in whole genome sequencing, again nicely documented by Olaf and Professor Cooper, by the various penetrants of mutations which we find in increasing numbers. Now, what are the key relationships of the European Society? There's a journal which you all know. You heard about RD Connect, but also we work with national human genetic societies, and it's quite a daunting task in Europe. It's not only EU 28 now, we have +1 with Croatia, but it's also with all the other countries in Europe, and it's 47 entities. And we also work in the International Federation of Human Genetic Societies, which, for instance, Egypt is part of India, but unfortunately we don't have any representatives from the Gulf. You can see that also we aim at developing services in a way that we harmonize curricula for postgraduate education in medical genetics. And here in green, suffice to say, then these are the countries which have medical genetics as a primary specialty. This is the duration, these numbers is the duration of postgraduate training, and the number of countries where it has not been established so far is decreasing. And of course, this model was, we will be happy to share also with the countries in the Gulf. Now, all of us who are working in medical genetics are usually viewed by our clinical colleagues, the mainstream field, you know, by urologists. Oh, you guys, you're the ones who deal with all these weird cases, syndromes, and things which are insignificant. But we need to bear in mind that rarity is precious, it's exemplary. And one of the founding fathers of modern genetics, per se, Francis Galton, said treasure exceptions. But I mean, the concept of rarity is much more older. And for instance, William Harvey, already in 1657, said quite rightly that the discovery of the usual law of nature by the careful investigation of cases of rarer forms of the disease. So this was very wise and prudent, and this is what we deal with in medical genetics, and this is what we would like to show to our colleagues in mainstream specialties. Now, what is the definition of a rare disease? I mean, it's arbitrary. It's 1 person in 2,000 or 5 in 10,000. It's in line with the European Medicines Agency regulation, which is instrumental in I would say, not only development, but regulation of orphan medicinal products. And as Olaf said, we have tremendous amount of rare diseases, but there are very few therapies available. And the field is very close to neurology. We know how to diagnose, and we diagnose well, but we don't know how to treat, or we know how to treat, but it's very limited. But also, not only patients do not want only I would say, etymological causal diagnosis, that is, that you have this and that rearrangement, this and that mutation, but they also want a functional diagnosis, that is, you know, how long my child will live, what will be the intellectual problems, will I see my child moving, playing, being emotional. And this is a thing which we should not forget, and we should always stress it's not only about chromosomes and mutations, it's the whole holistic view of the patient, as Olaf has nicely shown. Now, also, the European Union and the Commission recognized the definition, and basically all these European, I would say, documents, and I don't have time to go much into details, stress the translational aspects of rare disease, that is, from diagnosis to treatment. As Olaf has said, there are over 8,000 distinct rare disease entities today, extreme heterogeneity. Only few, you can see 250, are in the current disease classification. And it's obvious that if you have 3, 4, even 400 cases per country, that international collaboration is necessary, not only international within Europe, but also with the United States, now growing with India, now with China, and again, we would be very happy to work with the Gulf Cooperation Council. And since 80% of these rare diseases have a strong genetic origin, remember OMIM, that's more or less overlapping with OMIM. We as medical molecular geneticists are instrumental in their diagnosis, treatment, and as Ola has shown, in the broader management of those cases. Now, you can also see that the group is very heterogeneous, traditional syndromology, oncology, neurology, and so on. I don't want to go much into details, but this is the current, I would say, percentage-wise substructuring distribution according to orphanage, which I will touch upon briefly. I mean, all these rare disease initiatives are not only the privilege of Europe, but they also, the US was much further ahead of us. In 1993, they had the Orphan Medicines Act, and the Office for Rare Diseases is operating in NIH since 1993. And here are all the other documents and position statements and recommendations and so on, which are relevant to rare diseases. And the outcome of it is that by the end of this year, all European Union countries should have so-called national plans and strategies where diagnostics of rare diseases and treatment and so on should be implemented. Now, Orphanet is a one-stop portal for rare disease knowledge, to say in the broader term. So, for instance, it's centered around rare disease nomenclature. You can get a director of services, specialized clinics, medical laboratories, patients' organizations, and this is very important, as Ola has shown. And on research and clinical trials, you can go via genes. You can look what's available in the orphan medicine field. You can go by clinical science. It's not as POSSUM or London dysmorphology, but it's also very helpful. And you can also go by prevalence and so on and so forth. So I welcome you to visit the page. It's very simple, orpha.net, and each disease, for instance, has so-called identity card where you have all the additional information related to it. And as you know, our patients, when you at least suggest the diagnosis, it's a Google generation, and we see that in our clinic. They come the second day with their eyes wide open after overnight searching of the internet, being completely scared to death because the information is not curated, it's not validated, and of course the worst possible outcome sticks to their mind, and we need to deal with this. So we often link them to Orphanet, which is now available in 6 languages, unfortunately not in Arabic, but you can see these are the members of Orphanet who contribute data on rare diseases, and unfortunately, again, data from the Middle East are lacking. Now, Olaf didn't have time to elaborate upon it. We discussed in the morning. Here I wanted to show that Tübingen is one of the rare disease centers for southern Germany. We also have a rare disease center in Prague. And also there are various rare disease centers which are multidisciplinary. It's not only genetics, but it's also treatment. It's linked to all these orphan medicine initiatives and so on. And again, for the sake of time, I don't have much more time to elaborate on it. But if you link to the Orphanet website, you will see a lot of these documents where these individual networks or centers link to national networks, international networks, either on a group of diseases or even in the more common rare diseases such as cystic fibrosis on a disease-specific level. So again, I invite you to read all the useful documents on the user website where you have reporting initiatives and so on. It's very helpful because our societies are quite similar. The healthcares usually are quite similar, and the same applies to the Gulf. And again, it needs to be done here. You have a great research, you have a lot of things going on here, but you need to also invest into services. Now, Eurogentest, that's the second part, just very briefly. It's a European project, already running since 2005. The first version was Eurogentest 1. Currently, we are in the final phase of Eurogentest 2. It's a network of excellence with a splendid website. Here you can see the link. And the main objective is to measurably improve the quality and management and provision of genetic testing for the benefit of patients. I mean, it sounds almost too good to be true, and it's quite a daunting task because what we have shown for a number of years, the quality of genetic testing is not 100%, and we need to also be frank that there's a lot of laboratories which make repeatedly errors and so on and so forth, and we need to also inform the mainstream medical specialties that the data which you get out of genetic laboratories are not written or set in stone, and they can have errors and they have to be critical. For this purpose, you can also have a look on Orphanet. Eurogentest is linked with Orphanet, and you can see which laboratories are accredited to the international standards. And there are numbers of them, and again, I don't have time to dwell into this, but again, quality is of paramount importance. You need to provide within quality schemes external quality assessment, and again, just very briefly, these are the schemes which you can participate in. The cystic fibrosis one, for instance. Many of you know the European Molecular Quality Network, which Genetics Quality Network, or biochemical genetics here for cytogenetics. So all of you are welcome to visit the website and eventually register in these quality schemes. And again, you can see that quality is spreading in genetic testing, and it's also spreading to the Middle East. And you can see how the participants in various workshops organized, quality workshops organized by Eurogentest were coming from. Finally, there are patient leaflets. They are very useful. As I said, patients lack validated and well-written information. Over 30 languages are available, and today in the morning I was checking the website, and I'm pleased to announce that there's also Arabic. For instance, here you can see what is a genetic test. We also have Farsi there, Turkish, Bengali, and of course we would be now happy to include not only Chinese, which is there, but also, for instance, Vietnamese, and so on and so forth, in order to account for other populations where genetic services are developing. So, what to say in the end? As you all know, the future is bright. Everybody says that. But there are a couple of lessons which we need to bear in mind when we would like to apply all these splendid research developments into clinical practice. And again, as it was shown multiple times today, research does not equal diagnostics. Those are two domains which need to be reconciled. And for instance, Eurogentest Orphanet is working with a previous project called TechGene, where we were partners with Olaf, and where some of the partners then moved to RD Connect. And for instance, this is a symposium which will be held, in fact, at the end of this week. And it's a symposium, for instance, on the implementation of next generation sequencing. And again, it should not be broadly applied. Olaf has nicely shown the limitations, for instance, of enrichment, the incompleteness of the exome, and there are still many, many things to do. The other thing, which was beautifully exemplified by David Cooper, is that you need to bear in mind that there are population differences. This is one of the projects we were partners in, where you could see the differences between European populations according to typing of 350K SNPs in Europe. Again, suffice to say that more or less the geography in Europe, when you superimpose it on the so-called differences plots, here you have the Finns, here you have the Southern Europeans, here you have the Western Europeans, are more or less in line with basically geography overlaps with the PCO plots. To cut this short, so you really need to be aware of the population differences. Beautiful example again today in the morning on the Usher syndrome, and you need to work together. And this is, for instance, a project which I was involved in its coordination on cystic fibrosis, and numbers count. So, for instance, this is a collection of registries of European cystic fibrosis cohorts, again based on the age groups, and that's not important. But if you collect all the data in Europe, then you get over 23,000 patients, and all the American ones account for 24,000. In total, it's 48,000, almost 48,000 patients. And what this says is that all of a sudden the field becomes interesting for the pharma. And the pharma is now very interested in developing new drugs, new mutation-specific therapies. And for instance, this is the chart of the so-called drug development pipeline of the Cystic Fibrosis Foundation, which we work with. And you can see, for instance, all the various modalities, therapeutic modalities, from gene therapy through protein assistance and repair, restoration of salt transport, mucus treatment, anti-inflammatory, anti-infective, and so on. And as Olaf nicely shown, that, I mean, the big pharma goes by blockbusters, but the blockbuster drug development model is not that much working anymore, and what we see now is the slicing of the salami even thinner, and you have various other cocktails of anti-inflammatory agents and so on. But these drugs work only very, very much downstream from the genomics, metabolomics, and so on. Again, I don't have time to go into details, so they are very, very much touching the surface and are more or less symptomatic. But you really need to go down to the mutation and a specific pathway. And one of the most important drugs, which was hailed as a drug of the year of 2012, of last year's Kalydeco, which is a mutation-specific therapy aimed at a mutation which I happened to co-discover when I was a fellow at Johns Hopkins in the early 90s, the so-called G551D. And it was really hailed as a genomics triumph because this drug is really a miracle, because it's really aimed at specific mutation and a specific disease pathway. And it not only restores the sweat chloride concentrations to normality, but also reverses the lung phenotype and even reverses, for instance, the agenesis of vas deferens. So it's almost like a miracle drug. Patients were the ones who helped us, who also raised the money, but, and we don't have time for that, the price. The price is really pretty high, and it's close to almost $300,000 per patient per year, which is tough for most of the healthcare systems in the world. But again, if you return the patient back to work and he or she starts working, he or she will pay taxes, he will raise kids, and he will no longer be an issue for the social system. So, I mean, what you invest into therapy, which is highly targeted, yet individually expensive, will be offset by decreasing social costs. So, we are all here to provide guidance for our patients. Thank you very much.